Hello friends, today we introduce another important topic in probability theory, and this would be probably one of the last topics of discussion. This is going to be weak convergence and convergence in law. So far you have known the concept of convergence in almost sure sense and convergence in probability. You have seen their interrelations. You have seen that almost sure convergence is almost similar to the concept of pointwise convergence of a sequence of functions on a measured space, and convergence in probability is a slightly weaker notion. Now here we are introducing a concept of convergence that is very different from what you have seen so far. And so to motivate this, let us start with this example that suppose I have got x1, x2, xn, IID, n01. So I had given you as an exercise to verify that what is this distribution 1 by root over n x1 plus x2 plus xn. So I hope you have seen by now figured out that this follows n01 distribution again. This is the hint is to use generating function. Now I generalize the problem simultaneously slightly. Now my question is that suppose x1, x2, xn are a sequence of square integrable or IID random variables. Square integrable means these random variables have finite variance. Each of them has finite variance. And IID, let me add mean 0. Mean 0, square integrable random variables. That means each expectation of x1 is 0 and ex1 square is finite, and so are all the xi's. Now I ask what is the distribution of this same thing 1 by root over n x1 plus x2 plus xn. Now obviously the exact distribution will depend on the distributions of these xi's, but the most remarkable feature in probability theory is that for large n, we can approximate the probability distribution of 1 by root over n x1 plus x2 plus xn by normal distribution, irrespective of the distribution of x1, as long as this the variance is finite. Okay, and also the here I must say the mean is 0. Mean is assumed to be 0. So you see, as long as this is a remarkable result known as the central limit theorem. So that we will see after this discussion on convergence in law. So the reason I am telling you all this is that, see, what is the idea here is that I do not know the exact distribution of x1 plus x2 plus xn by root n when xi's are IID normal with mean 0 and variance is finite. Okay, but for large n I can approximate the distribution of this ratio by n01 irrespective of what the distributions of xn's are, as long as the variance is finite. So this is the basic concept. So this example motivates what I am going to talk. So weak convergence or convergence in law of a sequence of random variables yn to another random variable y on the same space. This implies that, so I will go to the exact definitions, but before that let me introduce it intuitively based on this example. So here, so what is my yn in this example? This x1 plus x2 plus xn by root n was my yn. So what I said is that I do not know the exact distribution of yn for each n, but for large n I can approximate the distribution of yn by the distribution of some y. So in that case, that sum y is the standard normal random variable. So we say that x1 plus x2 plus xn by root n converges in law or converges weakly to the n01 distribution or to a standard normal random variable, and that is the central limit theorem. So the idea of weak convergence is that the distributions of yn may not be known, but for large n we should be able to approximate this distribution of yn by some known distribution. So then we say that yns converge weakly or in law to that distribution or to that random variable. So pointwise convergence was that ynw goes to yw for every w. So here we are not talking about the convergence of the sequence ynw to the number yw. We are rather talking about each random variable has a probability distribution. We are saying that the probability distributions of yn can be approximated by some common distribution for large n. So this is a very different way of defining convergence, and it makes much more sense in probability statistics, because in probability and statistics we are most of the time interested in making probability statements like what is the probability that, suppose you want to find out what is the probability that yn is greater than a number yn is greater than number a. So you want to find that out. So to find that out, you need to find out note the probability distribution of yn. That may not be known, but weak convergence will ensure that for large n you could approximate this probability by probability of y greater than a, where y is some random variable whose distribution is So that is the utility. So that's why weak convergence and convergence in law is very useful in statistics, because here you are talking about approximating probability distributions by some known distribution, and quantiles of a probability distribution. So when you can approximate a probability distribution by some known distribution, you can also approximate its quantiles by the corresponding quantiles of that distribution. So here I am saying that it is weaker than the concept of convergence in probability. That is, I will give you an example where you do not have convergence in probability, and hence you do not have almost pure convergence, but you have convergence in law. So let us look at this example. Suppose z be a standard normal random variable, that is a random variable that is following n0 normal distribution with mean 0, variance 1. Now let us look at yn is equal to z. Okay, and so each yn is then following normal distribution with n01, and y is equal to minus z. Okay, so you see for each so if yw is 1, then this yw will be is, so if this ynw is 1, then this yw will be minus 1, so and vice versa. So you see point wise what is the difference, yn minus y, this is twice z. So now suppose for any epsilon positive, I want to compute probability mode of yn minus y greater than epsilon, then that would be simply probability of mode of z greater than epsilon by 2, right? Because this difference is twice z, where z is n01. Now you see that if I had convergence in probability here, what will happen? Then for every epsilon, this probability has to go to 0 as n tends to infinity. Now you see here that in the right hand side there is no n, so this is a constant free of n. So this is probability mode z greater than epsilon by 2. Now this cannot be negative because this is a probability. Now this may or may not be 0, that we will have to find out. Now we know that this is z is following standard normal distribution. So standard normal distribution is supported on the entire real line. So obviously when epsilon is large, so this probability will be small, but it will be always positive, because no matter how large your epsilon is, a normal distribution would always assign a non-zero probability above epsilon by 2 and below minus epsilon by 2. So this is a positive constant, and it does not vary with n. So therefore this probability in this example will not go to 0 as n tends to infinity. This is a positive constant. It will, for each fixed epsilon, this is one positive number that does not depend on n. So therefore we don't have convergence in probability. But you see what is happening. Each yn is following n01 and y is equal to minus z. That also normal distribution is symmetric. So minus z will also follow n01. So the yn and y are identically distributed. So you see, so this is an easy case of convergence in law or weak convergence, because each yn has the same probability distribution as y. So we can approximate the probability distribution of yn by y. In fact, in this case there is no question of approximation. Each probability distribution of yn is exactly same as that of y. So you have the ideal case that you can you can know the probability, you can approximate the probability distribution of yn by the distribution of y, as they are identically distributed, but still there is no convergence in probability. So that is what I have mentioned here. So now, so far I have given you an idea of what is meant by convergence in probability, but then I need to specify this this sentence that I am saying, that for large n approximating the distribution of yn by y. So what do I mean by that mathematically? So here is that. To do that, first I need to define the probability distribution, because you know that every probability distribution is uniquely identified by its distribution function or by its generating function. So you have to, whenever you talk about approximating the probability distribution of yn, you are essentially talking about approximating the distribution function of yn or the generating function of yn. One of them you have to approximate. So we will define it with the concept of distribution function. So let us recall quickly what is distribution function of a random variable y. So it is defined fy, probability y less than equal to y. And some properties of distribution function, well, I leave it as an exercise for you to verify that distribution function is non-negative. Obviously this is a probability, it cannot be negative. Non-decreasing, meaning if y and z are two numbers, y less than, then f of y cannot be more than f of z. Now this is obvious from the monotonic property of probability. That is, if A is a subset of B, then probability of A cannot be more than probability of B. Or right continuity. Right continuity, f is always a right continuous function. That means if I take the right limit f at any point, that is equal to fy. Okay, so that is slightly challenging. You have to use continuity theorem. So you have to take f of y plus 1 by n and take a look at that limit. So that is a hint I am leaving for you. And the third is f minus infinity 0, f plus infinity 1. What do I mean by f minus infinity? So this is limit z tends to minus infinity fz. And the f plus infinity is limit z tends to infinity fz. Now, please see that f is a monotonic function bounded above and below. Why? Because it is a probability. So it cannot be less than 0, more than 1. So monotonic function bounded above and below. So the limit film soup, these will be finite. So I can take these extreme limits, and this is a non-decreasing function. So the more I go to the left, it is decreasing and bounded below. So this limit exists, and the more I go to the right, it is non-decreasing and bounded above, and so this limit also exists. So this is 0, this is 1. So now I have a fair idea how the distribution function of any distribution would look like. So it would be between 0 to 1 on the y-axis. The values of this function will be between 0 and 1, and from left to right it will be non-decreasing, and it will be a right continuous function. So now we are in a position to define the concept of weak convergence. So yn is said to converge weakly to y, or convergence law to y, denoted by yn. So we write L to emphasize that this is a weak convergence if and only if, as n tends to infinity, f and y goes to fy at every continuity point of f, where fn and f are the distribution functions of yn and y. So here the important point is that I am not talking about the pointwise convergence of the distribution functions. I am saying that f and y has to converge to fy at each and every point where f is continuous. Remember, f is a right continuous function. For certain distributions, it may not be continuous at every point. So in that case, I am not talking about convergence at the discontinuity points of f. I only want convergence at the continuity points. So this will be clearer with this example. So let f be any distribution function of some random variable. So what distribution I don't know, just take the distribution function. So this is probability y less than equal to y. So now I define yn to be a random variable with distribution function f and y equal to f of y minus 1 by n. So okay, first of all I leave it as an exercise for you to check that this is indeed a distribution function, that is this satisfies these properties 1, 2, 3. That is f and y equal to f y minus 1 by n. So as a function of y, this should satisfy all these three properties. And now I leave it also as an exercise for you to now take the limit n tends to infinity. What happens? So see,